Hello, everybody. My name is Peter Warren. I am a graduate student at the University of Central Florida. I am currently pursuing a PhD in mechanical engineering. My main research areas include additive manufacturing, non-destructive testing and evaluation, machine learning methods and applications and how they can apply to those technologies, and also more broadly, turbo machinery applications. So the work I'm going to be presenting today is on the shrinkage prediction using machine learning for additively manufactured ceramic and metallic components for gas turbine applications. Okay, so this presentation is going to begin with a quick overview of sintering, get some of the basic sintering definitions out there and some of the basic physics that occurs during sintering, followed by the basics of additive manufacturing, and as it pertains to this work, that's mainly additive manufacturing for metallic and ceramic components and the techniques that are utilized for that. Then I'll talk about how this technology can be very useful for turbo machinery application. And then we'll get into the heart of this paper, which is utilizing machine learning to help predict the shrinkage that occurs during the sintering phase of manufacturing for these specific types of components. I'll talk about the methods for collecting experimental data, how we can apply machine learning methods to that data to better predict this complex physical phenomena known as sintering. And I'll talk about some of the Monte Carlo style simulations that we ran for this work to help generate data and the reasons why we chose to do that. I'll wrap it up with the conclusion. I'll talk about where we plan on going from here in the future. And also I'll acknowledge some of my co-authors on this paper and some of the people who helped me with this work. I'm going to turn off my camera now so that I can utilize the full screen for my presentation. Okay, so this slide will give us a quick overview of sintering. Sintering is a thermal process used to bond contacting particles into a solid object. Here we have an SEM of the early stages of bronze particle sintering. We can see them beginning to neck. That means the particles are starting to kind of merge together. Here we see the publications per year on sintering. So we can see an exponential increase in the interest in sintering here. Some of the common materials for sintering include metals and ceramics and polymers, mostly metals and ceramics. Density equals mass over volume. I'm sure everyone is aware of that, but density is often the optimization parameter involved in sintering. Higher density equals a better product in most scenarios. Porosity is the unfilled space. Powders are often bound together prior to sintering, and this can be done either by force, which is compaction, or with a binder material. And in additive manufacturing, you'll normally see a binder material holding the metallic particles together. And this is one important definition. The green component is pre-sintered and post-binder. So typically in additive manufacturing, that means pre-sintered and post-printed. And prediction of the phenomena of sintering is very difficult due to so many different input variables listed here. Okay, so now let's quickly talk about the quantification of sintering. We can look at this graphic here to get some visualization of some of the definitions listed here. Grain size is the average diameter of the particles. As those particles combine, the average diameter will go up, so grain size will go up as sintering goes on. Grain boundary is the part of the particles that are in contact with other particles. Pore is just open space, and surface area is in purple here. That is the area of the particles that is not exposed to another particle, but is instead exposed to an open pore. So we can see that as sintering time goes on, grain size and density will go up, but porosity and surface area will go down. The stages of sintering include contact formation, followed by necking or neck growth, then pore rounding, so the pores will turn into small spherical voids, and the fourth stage is pore closure. Shrinkage is an interesting definition here. It is basically the dimensional change in a specific direction, and you can notice that it is the same thing as strain, which is interesting. You could almost visualize shrinkage as a permanent strain on the object. Here we have some examples of some graphs from the experimental data collected in this work. Fractional density and average grain size will go up as sintering time goes on, and normalized surface area will go down as the fractional density goes up, and it goes in a very linear fashion. Normalized surface area is current surface area over initial surface area. And again, we can see grain size going up as density goes up. Some quick background on additive manufacturing. Obviously, additive manufacturing has seen exponential growth over the past few years. This is expected to continue. As it sees more and more growth, the NDE required to certify parts that have been printed through additive manufacturing will go up as well. On this graph on the right-hand side, we can see data gathered through non-destructive evaluation techniques in exabytes. And as that data continues to go up and up, as these techniques become more and more refined, the realistic human processing limit will only go up in a linear fashion, or is projected to. A good tool to utilize in this scenario would be machine learning, because whenever we have a large amount of data, machine learning is a great tool to apply to that data, whether it be to make the non-destructive evaluation technique more accurate, or whether to make it more efficient. Machine learning can assist in both of those capacities. So I would expect that machine learning to be applied more and more to different non-destructive evaluation techniques in the future. Some of the advantages of using additive manufacturing with some of these materials is that it is faster to get a prototype out when using additive manufacturing. And also, in some cases, there is a higher design capability. In some cases, there isn't. One of the disadvantages, though, or two of the disadvantages for using metallic or ceramic additive manufacturing methods would be the speed of mass manufacturing is just not there. And also, there is a high cost of entry. So the additive manufacturing method that we looked at in this work is called FFF, which is fused filament fabrication. The specific printer that we used was the Metal X, the Markforged Metal X, and we printed a sample using that. It's a pretty interesting printer, as it does have a build wire similar to how FDM would work, but inside that build wire is basically metal particles that are already bound together with the binder, and it heats up, and the binder will I guess liquefy, and it will be extruded just as an FDM printer would. There are other methods to printing metal and ceramic components. One is BJT and one is SLS. I'm sure there are more, but those seem to be the three main ones, are BJT, FFF, and SLS. And for BJT and FFF, this is a pretty common cycle where we have a print, then we wash, then we sinter, and then you can finish it however. You can use hipping, high isostatic pressure, or machining. And this is an example of an SEM image of the sintered product. You can kind of see the grain boundary here. A lot of the particles have combined. There are a few pores, but not too many. And this is an example of it in the green state. Okay. So this slide is on measuring the sintering behavior of 17.4 pH stainless steel from a Metal X Markforged printer. At the top here we have the pre-sintered particles, pre-sintered SEM images, and that is the green state. And here we have post-sintered. And we can see some particles remained in between the layers of the print here. Maybe the sintering time could have been gone on longer in the future, but this was very few particles, and it seems like they just got trapped in between the layers there. But let's talk about grain size measurement methods. One is to just put a line directly through the image and count the number of grains on that line and divide that by the length of the line. Another method is to use image J and adjust the pixel threshold so that all pixels are either a 1 or a 0, a white or a black, and then divide all of those up into individual particles and take the average diameter of each of those particles. Here are some of the basic equations that help us to use grain size as a method for prediction of either porosity, which is epsilon, density, which is rho, and relate to that. And this equation here is a way to discretize grain size with time, and these equations just help relate grain size with density and porosity and sintering time. Okay, let's go over some of the experimental results that we got from this work. This is from the print conducted on the Markforged Metal X of 17.4 pH stainless steel. We determined a grain size horizontal and grain size vertical of 2.5 and 2.4 prior to sintering, and 23.3 and 20.1 after sintering. So we can see more shrinkage occurred in the vertical direction. And the reason that is because of gravity, the force caused by gravity, or also could be because of the layers and the method at which it prints. But we can see a discrepancy in the two values there. And the total number of data points was 6,420, and that is because for each image we can take a grain size measurement at each line, each pixel line. So if it's 1280 by 860 pixels, 3 total images before and after, then that's how many measurements you would get. These data points are in the same general area, so it could vary if the geometry was more unique, but in this case it was just a fully filled cube. But if you can see, if you did these different infill parameters, here we see an example of that from a CT scan that we took. If you had this unique infill parameter, it may not shrink the same in different areas of the unique geometry, and that's why we need to not just use a macro level approach to quantifying shrinkage during sintering. Complex geometries do not scale uniformly. One measurement scale, which is a macro scale, will fail to predict non-uniform shrinkage. So a multi-scale approach would be better for decreasing the prediction envelopes for shrinkage behavior. Okay, so I will quickly go over the basics of machine learning and some of the more common methods of machine learning. Basically what machine learning is traditional programming flipped on its head, where instead of having data input and writing a program for that to get to the output, you have your data input and output, put that in a machine learning algorithm, and write the program from the data. Regression is one method of that. It's kind of the most fundamental method. It's good at predicting a single dependent variable. In this case, we're looking at density or shrinkage as the single dependent variable. And a multivariable regression allows to incorporate multiple independent variables when making that prediction. So it is a good method to use for this sintering trajectory prediction. The neural network is more complex and may need to be utilized in the future. It is not necessarily very mathematically complex. It's ultimately, the way I like to look at it, is just a very fancy function approximation machine. And we may need to use that in the future, but we did not use it for this work because we were mainly looking at sintering trajectory predictions. We could see two examples of that, or two graphs showing different materials that are illustrating the sintering trajectory here, where we have grain size on the y-axis and sintering time on the x-axis here, and we can see a linear relationship. And part of the reason why that linear relationship occurs is not necessarily because of the physics, but because when you have this type of distribution of data and you take the log of it, that's actually a very normal technique in machine learning, is to take the log of any distribution to create a more normal distribution. So then it becomes more linear because of taking the log. If you didn't take the log of both of these variables, then it would not be so linear. But relative surface area and fractional density does already on its own have a linear relationship. Now, optimization of sintering can include 1, the maximization of density, 2, the minimization of sintering time so that you don't have to use as much energy, and 3 could be to accurate, and that's what we're kind of going for here, is to accurately predict the shrinkage for specific geometries, because in additive manufacturing you're going to have these new and unique geometries fresh from the printer. So this slide kind of illustrates exactly what we want to do using pictures mainly. So we have intricate STL components, and we run them through a digital version and create simulated data. We want our algorithm to learn from that simulated data, and then when you again have your STL, which is your print file, your part file, you can send it into the real version. It can apply the correct sintering trajectory, sintering parameters to it, and you can get dimensionally accurate final parts. So the input data for this work was grain size, surface area, and density measurements, and the output data was shrinkage data and porosity. That's what we want to predict. Ultimately, what our goal would be just to input more material parameters, powder information, oven conditions, all of the input data that you can put into it, feed that through, and the output would be material properties and final dimensions. So final dimensions encapsulates shrinkage data and porosity. So that's what we did in this work, and this slide kind of illustrates that. We have the error estimation of sintering parameters. Here we have the equations for grain size, and here we have the equations for surface area. Again, the grain size equation is cubic in nature and can be discretized using this version of it. The properties that we found experimentally were used to get this plot and to obtain the value for K, which is the sintering dependent parameter. Here we have time, sintering time, which was a total of 24 hours, versus grain size. The final grain size was 22.5 microns, initial 2.5. That gives a value of K equals 7.5. And here we can see the normalized surface area, which is current surface area divided by initial surface area. And we can watch as that goes down here. It has 2 fitting parameters, A and B. Those were experimentally determined to be 3.3 and 3.6 about. And the initial surface area is 0.6, and it actually goes to 0. And then it's unable to predict that final, 5 to 10% of shrinkage, because it will actually go into a negative, which is impossible. You can't actually have a negative surface area. So surface area is actually only a good prediction of sintering up to either 90 to 95% of fractional density. So to code the Monte Carlo simulations that we did in this work, I used NumPy, Matplotlib, and sklearn. The coding was done using Anaconda GUI. All the code is available on GitHub. It's broken into 3 parts, which is grain size measurement simulation, surface area measurement simulation, and error visualization with plotting. The measurement simulation is performed on SEM data generated through ImageJ. So basically just artificial SEM data. So from that data that is generated from the code that we just saw, we can analyze that data and create sintering trajectory predictions using grain size measurement and surface area measurement. In this graph here, we can see the prediction error in K in a percentage based on the standard deviation that is in the grain size measurement. We can see that you get dissipating results the more measurements you take. Your error is only going to go down by less and less as you take more and more. 2 measurements indicates before and after sintering. 3 would indicate stopping the oven to take a measurement mid sintering, and 4 you'd have to do that twice. So basically you can judge how well you want to know your sintering trajectory and perform that amount of measurements to accurately predict your sintering trajectory. The same thing is done here with surface area, except for this one, the number of measurements is plotted on the x-axis, and I just varied the standard deviation in the measurement pool for different lines here. So you can kind of use that code to vary the standard deviation in your measurement and get a good idea of how well you can see the sintering trajectory, and then you can optimize the sintering trajectory based on that data and adjusting those parameters. So if we want to take those grain size measurements and grain size equations and expand them to 3 dimensions, we can do that using these equations here. Just basically break it apart and separate K into 3 different X, Y, and Z directions. Here's a graphical illustration of that. The reason that is a good first step but not a good final step is because if the geometry is very complex, just breaking it into 3 of the cardinal directions there may not be enough in order to accurately predict how it's going to shrink if the geometry is unique. In order to do that, we may need to discretize the system and break the kx, ky, and kz into a function of the x, y, and z of the full geometry. So k needs to be an actual function of its input parameters, and that would be 3 separate functions for the x, y, and z direction. In this case, that's when it would probably be a better idea, because in order to approximate that function would be to use a neural network, because regression may not work as well. But we will try both of those in the future. So 3 conclusions we can take from this work is that typically stopping the oven more than 1 or 2 times does not increase your ability to predict K, A, or B by that much. So 1 or 2 stops should be sufficient unless you want a very accurate prediction of the sintering trajectory. Another conclusion is that the physics of sintering is very complex with a lot of parameters, and machine learning can be a great tool to help assist and create more accurate models of this process. And third conclusion is that grain size is a very good tool to help understand sintering and help optimize the process. Surface area, unfortunately, is not as robust as grain size, and maybe not as good of a tool to, especially when you're talking about getting from 90% to a full 100% dense object. So here are some of the works we plan to go into in the future, and that is first and foremost to expand to a 3D model with our predictive capabilities, maybe implement a neural network or convolutional neural network wherever that may be necessary. We want to incorporate more properties into our model, which could be sintering conditions, definitely input powder conditions, you know, what's powder size, powder geometry, distribution, all of that stuff, and then also incorporate input geometry as well. 3, 4, and 5 are kind of our experimental plans moving forward. We have like 64 different samples that are currently in manufacturing to provide us with more data. They have unique geometries, diagonal cooling holes, vertical cooling holes, horizontal cooling holes, and we may vary the max sintering temperature, sintering duration, and we will vary the geometry. We're also going to compare some different printers, the Markforged Metal X, the X1, and we may even possibly do some work with SLS as well. And we will conduct the same experimental procedure as we did with our first sample, which would be using MTS machine, SEM, XRT, CT scan, and many other experiments to gather data from these samples. Here are the references that I used for this presentation, and also the GitHub code. So a quick thank you to everyone who helped me with this work. Nanhini Raju has worked very closely with me on this project, and she submitted a paper to the Turbo Expo as well. She's helped me tremendously in this work, and it's been very good working with her. Milos, Hossein are my lab mates, and they helped me with this work. Dr. Subramanian, Dr. Kapat, and Dr. Ghosh also helped me with this work as well. So a big thank you to all of them. This work was done with the Cater Labs at UCF, the Cosmos Labs at UCF, and Siemens as well. Okay, thank you for watching my presentation. I hope you enjoyed it, and have a good day.